tutors get that other people don't. At the end of the quarter, the MSI tutors run a review session, and you can't go to it unless you've been going to MSI. Is that correct, Kyle? On the other hand, my last lecture will be nothing but here's all the things you need to know to get 100 on the final. Okay? So there will be a review session for everyone. It will be the last class of the quarter. But if you want further review and you want to go to MSI, then you can. It didn't happen this quarter, but suppose you were planning on failing this class. I don't know why you would show up on a Wednesday if you were planning on failing this class, but maybe you have some friends who want to take CE16 next quarter and are scared shitless. ACE is going to offer CE16 courses sections next quarter, just so you know.
If that was the case, I would have made a different decision last week and just take it.
It's the time in the quarter when people panic. We're heading towards the home stretch. I understand that. If you're the kind of person who shows up on Wednesday, my suspicion is you're okay. Ooh, I want to start warning you guys, there are assigned seats for your final. Please plan on showing up a half an hour early for your final so you can get your seat. I may give you your seat ahead of time. Your final exam asks what row you are in, and if you are in a row that is not assigned to you, that's an academic integrity violation and you risk getting a 0 on the final. That is to say, you do not get to choose to sit next to your best friend. Why do I do that? Well, one quarter I had a particularly egregious cheating situation going on, and I decided to experiment with giving assigned seats for the final. That quarter, a new class of student appeared, a class of student whose average on the quizzes was 9 point something and totally bombed the final. I mean, like statistically significant increase in that kind of student. That kind of student persists in all classes I've given assigned seats for. My model, which could be wrong, but I have no contravening information, is that people who are addicted to sitting next to their oh so good at discrete mathematics buddy, maybe even not noticing that they're accidentally incorporating information on the final, can't sit next to their buddy on the final. And so while they can maybe unknowingly copy during the quizzes, they can't during the final. Yes? Oh, okay. He would like you to sit with him.
You asked about a guy, the tree branch guy?
Oh, wait. Where's tree branch guy? Matthew? Matthew Harkins, I'm worried about you. I want to know that you're not under some vicious ant somewhere. Sylvan, whatever. If someone knows Matthew, could you get him to send me mail or something? Why are we talking about that? Oh, where was I before that? Cheating. Please don't cheat. Oh, God, I hate it when you cheat. Also, just touching your phone during the final, that's the end. You get a 0. Bye-bye. Okay? I had a student texting in Chinese, swearing up and down to me. It was all about what they were going to have for dinner, but guess what? My TA spoke Chinese, and that's not what it was about. So basically, I don't care if you're using code for, what'd you say?
We're gonna write some.
Yeah, I can't write in Farsi, I can't read Farsi, but I can find someone who can read Farsi.
Tap out Morse code.
No, Farsi is what they speak in Iran.
You're going to get partisan on that.
We have a lot of Iranian students in the School of Engineering. Don't cheat. You have assigned seats for the final. Please show up early. Oh, and you need your ID to get in. I'm really sorry, but when a class this size, like I'm looking at a guy back in the row, 3 rows back, and as far as I know, I've never seen your face before. I mean, you're here on Wednesday, therefore I love you, but I don't know all of you. So we have had cases in the School of Engineering where someone paid someone else to come and take the final for them. C16 is filled with stuff that is trivial if you've learned it and really hard if you haven't. And it's all really crucial for follow-on courses in computer science. You first. Is my mic on? Is my mic on? I think it's on. I think the volume's down low. Do you want me to turn up the volume? Yes, I appreciate it. The mic is on. Okay. Oh, did you see the cast list for the Star Wars movie about Han Solo? Oh, I'm so stoked. I'm in love with Donald Glover. Just in love with him. There was another arm. Did you want to ask me about my mic too? Okay, so assigned seats, MSI, you've already got the extra credit. Possibly there's room in MSI for you if there wasn't room before because some people may stop going. If you're freaked out, calm down a little bit. Oh, and I always have a special deal that says if you actually, there is a class of students who turns in homeworks, that's important, turns in homeworks, at least some of them, does very poorly on all the quizzes and aces the final. That student will pass, probably not a high grade. I'm telling you that no matter what your quiz average, even if it was 0.2, if you get at least 85% of the final, I will pass you in the class. Okay? That's a promise. That is to say, material from each quiz topic shows up on the final. You need to really learn the quiz topics and some things that had no space. For example, I never gave you a problem on divisibility because there wasn't enough room. I wanted to do a proof and I had to either pick congruence and modular or divisibility, but I would feel completely justified in putting, do you remember that slide that got posted to the forum, the right to get it wrong slide? It was taped. I would be delighted to put that exact problem on the final, okay? So let us, oh, is Allison here? Allison Campos? You get 5% extra credit. Okay, we're here, applied discrete math. There's only, by the way, there's only 5% extra credit. If you did the learning support services and you did MSI, you still only get 5%. Okay, final, assigned seats, Tuesday, March 21st. Do not leave for spring break before that or I will fail you. Mathematical induction, oh my God, mathematical induction is great. It uses well-ordered sets. Oh, that's awesome. It's basically just a rule of inference like the others. We are going to do proofs by induction. We're going to use the brain-dead theorem. I promise you, you can use the brain-dead recipe. You can use the brain-dead recipe even if you don't understand induction. On the other hand, this from your book is actually good information. I'm only saying the only reason I have the much simpler brain dead for the inductive step is that it has some simplifying assumptions and it gets you started. Everything on there is correct. Express the statement as for all n greater than or equal to b and then prove p of b. You know, instead of saying prove p of 1, it says prove the least element for whatever set you're ranging over. Write out the words basis step. That's great. Write out the words inductive step. Identify your inductive hypothesis. Identify what you're trying to prove. You know, this is all real stuff, and it looks intimidating until you understand induction. Once you understand induction, it makes sense. Oh, she says, that's great. She says, once you already know the stuff, you can understand it. I know, teachers say that all the time. But what I'm telling you is if you become comfortable with the brain-dead recipe and you do a few simple inductive proofs and you go back and read this, which is from your text, it will all make sense. Okay? This should all make sense to you now, I hope. And if it doesn't, we should talk. Maybe in class, maybe not. Now, last time I started doing a bunch of inductive proofs, and I spent the entire class proving that n is less than 2 to the n, something you guys probably already believed. But here's another inequality, and I could prove that. And I could prove this one that says that n squared plus n is always even. And I could prove this one that says that 5 is always evenly divide 7 to the n minus 2 to the n. I could prove to you that induction works, or I could start talking about the harmonic series. I want to do all of these things, but I'm not sure I have time for all of them. I would like your permission to jump ahead to start talking about the harmonic series because I looked for it online, and the way I want you to prove it is not available online as far as I can tell. Now, if my MSI tutors happen to find the way I want to prove it online, I'd be pleased as shit. But you could make it online with, you understand it by now, for sure. Kyle, if you would make a forum post, I would be ever so grateful. In fact, here, Kyle, is a present just for making a nice forum post about the harmonic series. Sammy the Slug, just for you, laser printed. That is a laser printed Sammy the Slug, straight from the IEEE to you. I paid $3 for that, so assuming that it takes you an hour to make that forum post, I am like a slave driver. Okay? Do we have a deal? Okay. So, oh my God, I don't know why there's a white triangle in the mist. Let's talk about the harmonic series. That white triangle is not, white rectangle is not supposed to be there. What's wrong with her? She thinks that's a triangle. This explains many things. Okay, so harmonic series, the number is important. H of 4 means add up the first 4 fractions. So 1 over 1, 1 over 2, 1 over 3, 1 over 4. So guess what H5 would be? Add one more and it's 1 over 5. When you say the harmonic series diverges, what you mean is you can eventually add up enough of these things, even though they become vanishingly small, to get to as big a resultant sum as you could ever want. That's the definition of divergent. There are some things, like if you, instead of having 1 over I, you have 1 over I squared, it will, no matter how many you sum up, it'll never be greater than 2. But the harmonic series, if you want to add, you can add up enough of these things to reach 1 billion, or 10 billion, or 1 billion billion. So that's, I want to talk about the harmonic series diverging and a particular way to prove it. The reason I want to do it this way is that it involves becoming better at manipulating sums in a way that is going to be exceedingly useful and pertinent for the large portion of the class that does not include Jesus that are moving on to CS 101. I'm sorry, electrical engineers, this is probably less pertinent for you. On the other hand, it's cool, so why not? Okay, so what we're going, this is a way to talk about the harmonic series diverges. The harmonic series diverges. What you're saying is, no matter how large, let me get a color other than black, no matter how large you want the sum to be, I can tell you how many things to add up to get that big. So n could be 5, n could be 17, n could be 1,000, n could be 1 billion, n could be 1 billion billion. K sub n is the number of elements of the harmonic series you have to add up to cause the entire sum to be at least n. Okay? Does this definition make sense to you? And yes, take notes, but it'll be, of course, online. Now, as you're trying to do this, it turns out that there's a way to kind of estimate how many elements you have to add up to get to n in terms of how many elements you had to add up to get to n minus 1. Your little induction detecting ears should be ringing here.
Sort of.
So, suppose you want to know how many, yes? Which, the top guy?
Yeah.
For all n, element of the natural numbers, there exists a constant related to n, such that if you sum up the first constant number of elements of the harmonic series, it will be greater than n. Another way to say this is you can cause the result of the adding up elements of the harmonic series to be as big as you want. Okay? And we can find the constant, or a constant, because we only say it exists, right? And there could be more than one answer. So suppose you want to have the elements of the harmonic series be at least 1. Well, guess what? All you have to do is add up to 1, and it's at least 1. The first element of the harmonic series is 1. If you add from 1 to 1, you get 1, and that's greater than or equal to 1. Woohoo! Suppose you want to get greater than or equal to 2. Well, 1 plus 1/2 plus 1/3 plus 1/4, it turns out, is greater than or equal to 2. In fact, it is 2.08. Now, suppose you want to get greater than or equal to 3. Well, if you add up the first 11, you get 3.01987. But that doesn't sound like a very interesting series, 1, 4, 11. What if you add up the first 16? You get 3.38. Ooh. Guess what? If you add up the first 64, it's greater than 4. It's 4 point something. If you add up the first, what is 4 times 64? 256? Yeah. If you add up the first 256, it's greater than 5. If you add up the first 1024, it's greater than 6. 6 something. That is to say, this is working very informally. We have a hypothesis. I'm just bringing you through it. You would not be expected to derive this. I'm bringing you through to say, guess what? Every time you want the result of adding up members of the harmonic series to be an integer greater, no problem. Just add up 4 times as many elements of the harmonic series. You want the harmonic series to sum to greater than or equal to 1, add 1 element. You want it to sum to be greater than or equal to 2, add 4. You want it to sum to be greater than or equal to 3, add 16. You want it to sum to be greater than or equal to 4, add 64. That is to say, we are hypothesizing and have not yet proved that this right here is true as long as k sub n is equal to, well, k sub n plus 1 is equal to k sub n times 4. We haven't proved this yet. This is a conjecture. This is a conjecture. And guess what? We're going to prove it. Okay? I have put this proof on either the quiz or the final or both for every CE16 class I've taught for the past 15 years. Kyle, how many of my CE16s have you been the MEP person for? I mean, MSI person for? This is the 3rd time? And how often does the harmonic series come up out of those 3 times? Every time. But there's all sorts of really good techniques that come up a lot. You've taken CS 101. You probably had to estimate sums with least bounds and upper bounds and all sorts of good crap like that. So yes? There are trivial methods to prove this that do not involve induction. The whole point is I want you to do a proof by induction. And in fact, I will phrase it in such a way that you have to do it my way. In particular, the easy way of doing it doesn't involve any induction. It doesn't involve a KN. You may have seen other methods of doing this online. There are papers online, which I've spent way too much time reading. The top 16 ways to prove that the harmonic series diverges. That's a real paper I read. They don't use our method. But what? How fucking dare they? I know, see, here's the thing. I know you guys laugh when I swear. It's like I'm Betty White or something. So it's a cheap laugh. I apologize. But you know what? I have no shame. So this is what we're going to try to prove. Oh, look, I've got another stupid white rectangle. Let me try to fix it. Says, we're going to prove for all n element of the natural numbers, there's always a constant related to n, which is also a member of the natural numbers, such that if you sum the harmonic series up to that constant, it'll be greater than n. Another way of saying this is you can make the harmonic series result of summing elements of the harmonic series be as big as you could ever want it to be. Another way to phrase this is that the sum from I equals 1 to infinity of 1 over I is greater than or equal to infinity, or greater than. We shouldn't say equal to ever. That's another way to say it diverges, but that's very informal notation. Why? My 3-year-old son knew. Why? Because infinity is not a number, it's a limit. Okay? But in the same way that you have no such thing as infinite integrals either. So anyway, we're going to have a base step, we're going to have an inductive step, and we're going to use a lemma. Let's talk about our lemma. Okay, here is, you recognize that font? This is a screenshot of one of my previous quizzes. So this explains why you have to use the method that I talked about. This was, see, look, it was only 4 points. There was another 6 points. Okay, show that the sum from k sub n plus 1 to 4k sub n of 1 over I is greater than or equal to 1. And then I said for 2 points, show that it's greater than or equal to 3/4. This is the lemma that we're going to use to prove that. Let's do the lemma first. Okay. Suppose if you're adding up sums of 1 over I, looking like this. So here we have 1. Actually, well, we're starting in the middle. We're not starting with 1. Let's start, we are at something we were calling k sub n plus 1, and we're going up to k sub n times 4, right? Okay, so 1 over k sub n is this much. 1 over k sub n, the quantity plus 1, would be this much. It'd be a smaller number, right? As the numbers go up, the 1 over that number goes smaller. So 1/3 is less than 1/2. 1/4 is less than 1/3. 1/4 is less than 1/4. 1/5 is less than 1/4. For some reason, this is something my brain is not doing well. Okay, but you see, you're adding up a smaller slice every time, right? Now suppose, let's blow this up and look at it bigger. Okay, so we have a block, and then another block, and then another block, and then another block. Okay, now suppose we're trying to look at upper and lower bounds of the amount of area in that block. So you could say, well, it has to be greater than or equal to if you added up the smaller thing each time. And it has to be less than or equal to if you added up the big thing each time. Oops, that was very ugly. The big thing each time. Is that better? That's better. Okay, someone who said, can we prove it using integrals? You see why that's, if someone in this area said, you see how that's similar? Yeah. Okay, so what we're saying is that if you go back to this picture right here, the amount of times that you think of this, computer programmers, most of you are computer programmers, even Jesus probably doesn't completely disdain computer programs, even though he's a hardware kind of dude. If you have a sum that goes from 1 to 3kn, how many times are you adding shit up? 3kn times. Does that make sense? So, like, I'm going to erase this, but a sum from I equals 1 to 10 of I, how many elements are you going to add up? 10. Okay, suppose we're talking about the sum from I equals m plus 1 to m plus 10. How many times are you going to add stuff up? 10. It's exactly the same. So what I mean is, if we're looking at a sum that goes from k sub n plus 1 to 4k sub n, and we just want to know how many times are you adding crap up, that would be the same as adding up from 1 to 3k sub n. Do you see what I mean? You're going through this loop 3kn times. Am I making sense, guys? Yeah. Okay. So each time you're adding up a thing. If we are looking at upper bounds or lower bounds, we can get the lower bound by always adding up the smallest thing you ever add up. So instead of adding up tiny thing plus tinier thing plus tinier thing plus tinier thing, let's just multiply the number of times you're adding things times the tiniest amount you ever add. Your result has to be greater than or equal to that. So for example, here you're adding something up 3kn times, and that thing is 1 over I. What is the smallest thing you ever add up? 1 over, well, no, let's look at this one. The smallest thing you ever add up is 1 over 4kn. So you're going through this loop 3kn times, and you're always adding up at least 4kn things. So the kn's cancel out, so that sum you're adding up has to be greater than or equal to 3/4 or 3/4. So if that made sense to you and you repeated it, then you would have gotten 2 points on this quiz, right? But it's not good enough because you want the full 4 points because you want to live life with all the gusto you can, going for the points on the quiz and going out and getting drunk afterwards. Yeah. I had sake last night. Yeah. No. Oh yes. For that.
Is this the lemma?
This is the lemma. There are lots of resources that talk about estimation of sums by always adding up the smallest thing or always adding up the largest thing. If you want a lower bound, then the number of times you add crap up times the smallest thing you ever add up, that's a good lower bound. And if you want an upper bound, the number of times you add crap up times the largest thing you ever add up is a good upper bound, right? It's kind of like taking this picture here that varies, and you get the green box or the red box. Does that make sense? Now, just this, using this particular method to prove the harmonic series, no, except that in exchange for this fine, extremely valuable laser printed $3 slug, our delightful MSI tutor is going to write the world's best forum post on harmonic series. As an inductive proof. The lemma, you don't need induction. We're going to use the lemma as part of our inductive proof, but let me tell you, the lemma is the hard part. Once you understand the lemma, using it is just straight brain dead recipe. So here's the thing. When we go back, all I got us last time was the 2 points. Here's the deal. It turns out, oh, let's go back to this picture. So in this picture, I estimated with either the red box or the green box. What if instead I broke the sum in half, right here? And I said, okay, let's take the minimum element in this part and the minimum element in this part. Now you still have a lower bound, but you have a better lower bound. That is to say, if you add up those two blue rectangles, you'll have a larger number than if you look at the area of the red rectangle. Because the best answer is you look at each element of the summation separately and you add them all up, but that's very time consuming. If you start estimating by saying, oh, that's way too hard, let's just always take the smallest thing we ever add up. Well, but if we break the sum in pieces, we're still doing less summing than we would have to do to actually go through it k sub n times, but we're getting a better bound. So that if we go back here and we break the sum, we say, let's take the summation from I equals k sub n plus 1. And why I start here and go to 4k sub n is what we'll talk about on the next slide. From 4k sub n of 1 over I, let's write it as the sum from I equals k sub n plus 1 to 2k sub n of 1 over I, plus the summation from I equals 2k sub n plus 1 to 4k sub n of 1 over I. All I did was break the sum not in half, I broke it in 1/3, 2/3. Okay, so what is, for this guy right here, how many summation thingies get added up? The answer is k sub n. What is the smallest thing that's ever added up? 1 over 2 k sub n. Okay, next part. How many times are you going through that add shit up loop? 2 k sub n. And what is the smallest thing that you ever add up? 1 over 4 k sub n. Okay, these k sub n's cancel out just like they did before. I have 1/2 plus 2/4, also known as 1. Remember, this became an inequality. So that means that the sum has got to be greater than or equal to 1. We did a lower bound analysis. Here's one of the reasons I'm doing this way. Lower bounds, upper bounds, that's what CS 101 is about. At CS 101, if you think this class is hard, let me tell you. Kyle? But let's just put it this way. If you learn it now, CS 101 will be so much more comfortable for you. And generally, the failure rate for CS 101 is higher than the failure rate for CS. It depends, CE 16, it depends on who's teaching it, though. Some people don't fail anybody. You want to know who they are, don't you? Your fellow students know, I promise you. Yes?
Since you theoretically do this, so you broke it out into 1/3 and 2/3, could you do it in 3 1/3s?
Yes, you could, but here's the thing. Do you remember when I told you that to prove something by induction, you have to have the exact form of the inductive hypothesis? So proving that it's greater than, for example, 1 1/4 won't help you because you're going to need to show that that 1 is going to come in very important for our inductive proof. If we just believe this guy, if we have proved this part, because that's what we did. See this right here? We just proved this nice lemma. We're going to go back to our inductive proof. Let's do it right now. I know some of you are only hanging on by your fingernails. Let me do it and then ask your question. Do you hear me, Joe? Is that okay? Please. What? Last slide. Okay. What about it?
So in this case, we don't have the basic step, right?
No, this is not an inductive proof. There's no basis step because it's not an inductive proof. Let's do an inductive proof now, okay? So basis step would be when n equals 1. So what we're saying is there exists a k sub 1 such that the summation from I equals 1 to k sub 1 is greater than or of 1 over I is greater than or equal to 1. We know that k sub 1 exists because we already figured out just a few slides ago that the sum of the first 1 harmonic numbers is equal to 1. 1 is indeed greater than or equal to 1. Okay? So k sub 1 equals 1. And now we are going to assume that that little back of the envelope guessing we did on this page works. And we're just going to assume, and you're allowed to do this on the quiz, that k sub n plus 1 is equal to 4 times k sub n. Okay? So what that means, and I'm going to write down the summation from I equals 1 to k sub n plus 1 of 1 over I is equal to the summation from I equals 1 to 4k sub n of 1 over I. Okay, according to the brain dead theorem, what I need now, remember the brain dead, here we start with this guy. Now the brain dead theorem says we need to have the left-hand side of the inductive hypothesis, which is effectively this. This is the inductive hypothesis. Oops, I should do the whole thing. the sum of the first k sub n harmonic numbers is greater than or equal to n. We're doing induction over n. That k is just a constant. By the way, are you reading Reddit? No. No. What book did you use for 101? Did you use Corman, Lyserson, and Revest?
I don't remember.
Was it a big white and green book?
I only had a PDF.
Oh.
You stole it.
It happens the most common algorithms book is Corman, Lyserson, and Revest. And I learned to do, I picked up this proof when I was teaching 101 using Corman, Lyserson, and Revest. It's in a footnote. But I thought it was cool. Yes? Alex. Ha.
No, that's good, because my mom.
Because I think of dead parrots and what?
Oh, my poor mother. Why does k sub n plus 1 is equal to 4 k sub n?
Because of our realization when we were playing around with backs of envelopes earlier, that if you always added up 4 times as many things, you would get to 1 integer more of stuff. So you add up 1 element and it's greater than or equal to 1. You add up 4 elements, it's greater than or equal to 2. You add up 16 elements, it's greater than or equal to 3. You add up 64 elements, it's greater than or equal to, I've lost the numbers, but do you remember when we did that? Okay, so this proof isn't going to work if we don't use that. I would note, I'm not asking you to derive this. It took a clever little bastard to figure this out the first time. I'm showing it to you just as it was shown to me. It was one of those times, it may not be for you, but it was one of those times I looked at it and there was way too many subscripts.
Yeah.
And I kind of looked at it and went, and then when I forced myself to go through it and understand it, I went, oh, that's fucking cool.
Same here.
So I want you to get to that, because that point, that is what, if you're an engineering major, that moment better be almost as good as sex for you, because it can be really rare. Rarer even than getting laid, depending upon who you are. I mean, I want you to have a chance to have that moment of, oh, I was so intimidated by the damn notation and the stupid infinity and the inequality and the subscripts, but you know what? Oh, that moment, it's a precious moment. Every time that happens to you as an engineering student, you need to suck all the juice out of that moment. That moment will get through you times when all you want to do is throw your laptop at the wall and kick the oscilloscope and kill the people who wrote your compiler. Okay, let's keep going, okay? I want to do it and then have you see it, and then we can talk about it ad nauseum, okay? So, for no good reason, I am going to divide this, the summation from I equals 1 to k sub n of 1 over I. Why? Because I'm going to want to use the inductive hypothesis. Plus the summation from I equals k sub n plus 1 to 4k sub n of 1 over I. All I did was break the sum. Again, that's a theme, and today we're breaking the sum. But the brain-dead theory says, lordy, 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 here we have the left-hand side of our inductive hypothesis, right? So what that says is that means this is greater than or equal to n plus the summation from I equals k sub n plus 1 to 4k sub n of 1 over I. What does our lemma say about that? It says that means it's greater than or equal to n plus 1. Oh, sorry, the wrong way.
Yeah.
Sorry, I have a little problem with left and right. Say, do you see? Here's a few things I want you to understand. As computer programmers, once again, sorry, Jesus, but as most of you are computer programmers, this is like programming. Once you come up with the right procedure is trivial. Once you have the right user interface, you have the right helper theorem, the proof is great. That's all. There's nothing missing. That's the whole proof there on that page. And the only reason it's easy is because of our helper theorem. Our helper theorem says, you know what? Inequalities are great. Now, the person, I've forgotten who it was, but do you see how getting an even tighter bound, like say for instance 2, wouldn't be very helpful? Right? Because you're only done when your proof, when that thing in the purple box shows up in the orange box, so that the orange box has to look exactly like the purple box, only everywhere before you had an n, now you have an n plus 1. This is so important, I cannot overemphasize it. You're not done with your inductive proof unless your last line looks exactly like your inductive hypothesis, only everywhere you had n, you have n plus 1, or everywhere you had k, you have k plus 1, that kind of thing. Am I making sense? Actually. Okay. Okay. We just did it. That's all there is. There's no more. Okay, now what it is estimation of sum values. Look up lower bounds and upper bounds of sum values. Yes?
Question about the first one, because I'm not too clear about what exactly were you breaking up in order to get that.
I broke, okay, so here, let me help this way. I had the summation, oops, let's not do that. I had the summation from I equals 1 to 4k sub n of 1 over I. Are we happy so far? Yeah. Okay, now I have this marvelous lemma that I guided you through, and it starts with k sub n plus 1 to 4k sub n of 1 over I. What's left? What goes in this box? So now we want the summation from I equals k sub n, sorry, I'm writing it backwards. From I equals 1 to k sub n of 1 over I. That's the whole sum. That's all the sum elements. Here's another way to think of it. Summation from I equals 1 to 40 of 1 over I is equal to the summation from I equals 1 to 10 of 1 over I plus the summation from I equals 11 to 40 of 1 over I. Does that make sense? Sometimes real numbers really help. Oh, by the way, I found my copy of George Polya's How to Solve It, and I labeled it as please don't remove it from outside my door, and it's sitting in the pocket outside my door, together with the nuts and bolts of proofs. If you are feeling shaky about proofs, go spend an hour sitting out my office reading those books. It will really help you. Yes? Okay, let's go back and look. I've already used up all the laser printed slugs I brought with me though, so there's no prize.
So the 4k sub n summation plot equals 2k sub n and the I equals k sub n plus 1. Is that correct there?
It should be the quantity k sub n plus 1. It's not k sub n plus 1.
Okay.
So this right here, this is the summation from k sub n plus 1. See, I'm going out of my way to write a nice big plus 1 to 4k sub n of 1 over I. There's no k sub n plus 1 anywhere on this slide. Okay? Was that the error you thought I made? I didn't make that error except in terms of having severe hand-eye coordination issues. Yes? You.
Okay, on the previous slide, how would we know that k n sub 1 or k sub n plus 1 is equal?
Let's find previous slide. Do you mean this one?
No.
Do you mean this one?
Yeah. How would we have been able to find k n plus 1 is equal to k?
Well, I have two answers for that. Answer number one, you don't. I just tell you. Hey, guess what? This proof works if you always add up 4 times as many things to get to the next integer plateau. I say that to you. I say, well, clever little bastards who wrote Corman, Lyserson, and Revest figured this out decades ago. Let's use it. On the other hand, I did this to try to gently feed you through the process. Suppose it's remotely possible that someone in this room, maybe even in the second row, wants to be a computer theoretician someday. This is the kind of reasoning process that theoreticians go through when they're trying to figure out things. What's the pattern? Hey, let me try to figure out, is there a nice pattern, hopefully associated with powers of 2, because we computer scientists love powers of 2, just love the shit out of them. It turns out, for example, if you add up 1, it's greater than or equal to 1. If you add up 4, it's greater than or equal to 2. But then the pattern sort of breaks. You only have to add up to 11 for it to be greater than or equal to 3. But you know what? You add up 16, and it's still greater than or equal to 3. And if you check and you add up 64, it's greater than or equal to 4. So what I'm saying is that when a clever little mathematician slash computer scientist was playing around with these things, they said, you know what? I can really proof the hell out of this thing if I just go ahead and assume that k sub n plus 1 is equal to 4 times k sub n. It looks like it works empirically. Have I proved it? No. But you know what? One of the things you learn in computer science is there are problems that it is really hard to calculate, but significantly easier to check if you have a right answer. That's a class of problems known as NP-hard. And if you're going to be computer scientists, you're going to have to learn all about it. An NP-hard problem is one that it takes an exponential amount of computation to find an answer, but it takes a polynomial time to check to see if an answer is right. So what we have here is people playing around. You know, maybe they've been up all night, maybe they stink, maybe they've been living on Cheetos and Dr. Pepper. And they say, you know what? It looks like I could have a really simple proof if I just assumed. It looks like if I add up 4 times as many things, I get the next value. No, that's the quintessential computer science diet. I know all about that because I lived in Margaret Jacks Hall at Stanford for 6 years, eating whatever came anywhere near me. If it was in the junk food machine at 4 a.m., my standards would go low enough that I would eat whatever was in there. It's just life of grad school. There was a long way at 4 a.m. There's nowhere else to buy anything in Palo Alto. At least at that time, Palo Alto basically shut down about 7 or 8 at night. It was just gone. There was a gay bar in Redwood City, but that was a long way to go. Where was I? Proof. Okay, did I answer your question, fine gentleman in the back there? I can't. There you are. Okay, here's what I want you to generalize. Sometimes people play around and come up with a hypothesis that they didn't derive, they guessed at, and then an inductive proof showed them they were right. That's number one. Number two, You can find lower bounds for sums by just always adding up the smallest element you ever add. You can find upper bounds for sums by always adding up the largest thing you ever add. And you can find closer bounds if you break your sum in pieces.
And apply that same process.
And apply that same process. Exactly. Does that make sense? This one proof, there are simpler proofs of the harmonic numbers. Proofs that have been famous since the 1800s or before.
This uses strong induction.
But this uses, no, it uses weak induction.
Oh, yeah, that's right.
It uses the first principle of induction according to your book. It uses weak induction according to normal mortals that are not named Jacob Rosen. And Kyle is going to write the world's best forum posting about it.
Slight exaggeration, probably only a great one.
A great one is acceptable, well worthy of a slug. A great one would be well worthy of a slug. Okay, maybe tomorrow I'll go buy more slugs.
That's like 45 minutes of time, though.
By the way, I've had people ask about the cyber slug. You know, the slug that is using a laptop and has shades on? IEEE is selling cyber slug t-shirts this week in the bottom of Jack Baskin Engineering. So if you've always wanted a cyber slug shirt, now's the time to go get it. Google Calendar wants me to go to a meeting right now. Okay. Okay, let's do this proof, okay? I will review the harmonic series proof on Friday, too. And it has a high probability of being on a quiz. Okay, so let's prove n factorial is greater than 2 to the n. This is a little bit less trivial than n is less than 2 to the n, okay? And we're going to assume that it works for n greater than or equal to 4. The basis step, it says n greater than or equal to 4, so the value that we want to use as our lowest element is 4. So 4 factorial is 24, 2 to the 4th is 16. Hey, what do you know? 4 factorial is greater than or equal to 16. So we put a little red check mark and we're done. Or a black check mark, it turns out. Let me switch to red. Okay, induction step. We are going to assume that n factorial is greater than or equal to 2 to the n for, this is stated as a strong inductive proof, but we don't have to. So we're going to start out by putting k plus 1 factorial on the left-hand side. That is our, that's the left-hand side of p of k plus 1. Everybody see that? And then we're going to rewrite it so that we have k factorial times k plus 1, so that we have the left-hand side of p of k. Now, according to the inductive hypothesis, we know that k factorial is greater than or equal to than 2 to the k. So we're going to move to this inequality that we have here. And now we have that k plus 1 factorial is greater than 2 to the k times k plus 1. Right? When would we be done? We will be done when we say k plus 1 factorial is greater than or equal to 2 to the k plus 1. Right? That's all we want. So, since k is known to be greater than or equal to 4, I can just go ahead and replace k plus 1 with 2, and it's perfectly legitimate, right? So that means I now have it's greater than 2 to the k times 2. And 2 to the k times 2 is equal to 2 to the k plus 1. Right? Because remember, guys, 2 to the k is just equal to 2 times 2 times 2 k times. And if we add 1 more times 2, then it's just k plus 1 times. Make sense? Okay. At this point, I just want to tell you my expectations. If I'm wrong, please don't think I'm a bad person. This proof, although harder than many of the other inductive proofs you study in this chapter, is actually pretty easy once you become a little more comfortable with inequalities. This one right here. Yeah? It turns out we went over, last Friday we did like nothing but go over this, unfortunately. But it turns out with inequalities, you can replace stuff when it comes to inequalities. If you're on the small side, you can replace numbers with anything known to be smaller than it. On the big side, you can replace numbers with anything known to be bigger than it. I actually got quite a lot of feedback that my silly demonstration with height actually helped, which kind of amazed me. Suppose I owe you, say, you know, Aisha, I owe you at least $3. Well, if I give you 10, you're probably happy, right? So if I say I'm taller than Aisha, well, I can replace your name with anyone known to be shorter than you, and I'm still taller than that person. And you can even multiply. So for example, I could multiply by 1/2 on the smaller side, because that takes the thing smaller. The thing you have to be careful of, really careful of, guys, keep this in mind. If you understand this, you're in really good shape. Anytime you do anything with inequalities in any sort of substitution, you are going from a stronger statement to a weaker statement, and then you need to be really careful that you're moving forward in your proof, that you're never going from a weaker statement to a stronger statement. Because if we know that I'm taller than you, we don't know anything about my relationship to anyone who's taller than you are. So like, I think you're taller than she is. But we don't know for sure about my relationship to you, because we only know about my relationship to you and anyone shorter than you. Is that making sense to you? Is this making sense to you guys? I would write must be smaller than that, because k plus 1 known to be less than.
So just like on the side.
Right. Yeah. You have to basically, let's remember what a proof is. A proof is something that would completely convince a mathematically sophisticated person. Not an anal mathematically sophisticated person, just a mathematically sophisticated person. A nice, relaxed, mathematically sophisticated person is good enough. Do you see what I mean? You know, like, I'm not going to penalize you for misspelling a word on your quiz. You know, if you have an inequality and you replace 5 with something known to be less than it, and you use 4, then I'm going to know that you did that for a good reason. But writing on the side, replacing because known to be less than 5, awesome. And there was a question in this area. Was it you?
So was the k factorial replaced by k
Because of the inductive hypothesis. Because during the inductive hypothesis, let me state this again. The inductive hypothesis is a thing you get to believe is blessed canon during the inductive step. During the inductive step, you get to believe that the inductive hypothesis holds, and you must use that or it's not a correct inductive proof. So I ripped out the left-hand side of the inductive hypothesis and replaced it with the right-hand side, and since the inductive hypothesis involved an inequality, I had to use an inequality. Does that make sense to you? Are we doing well? The quiz, it's the time of the class where I tell you what's going to be on the quiz. There will probably be 2 problems. There will probably, one of those problems will probably mention the harmonic series. Okay? Both, you know, induction is going to be front and center. Inequalities are going to be front and center. Summations are going to be front and center. Okay? Yes?
Should there be strong induction on the quiz?
No, because I haven't lectured on it. You have not lost out doing a strong inductive proofs, I promise. It turns out, speaking as someone who seems to have done some strong inductive proofs as far as I can tell, strong induction proofs, once you get it, are actually easier than weak induction proofs because all it does is give you more things you can assume. That's all it does. So, see you Friday.
Where do you buy the shirts for the slug?
And you know where the coffee cart in the Baskin Engineering building is?
I can probably find it, yeah.
It's in that same hallway where